For finite element simulations, you often need non-manifold assemblies between two or multiple parts. In those cases, it's important that the interfacing parts have shared nodes in order to create realistic loading conditions. In this exercise, we will explain how to make non-manifold assemblies, create good surface meshes, and convert them into volume meshes, as well as assigning material properties to different parts with the Materialise Mimics Innovation Suite. We will use a vertebrae and invertebral disk as an example for this exercise. We will start with the creation of non-manifold assemblies in Mimics, since we can use masks as our starting point. Indicate the masks needed for the assembly and go to the FEA CFD tab and select Calculate Non-Manifold. Try to make your matrix as square as possible, as this will give good elements. Right-click on the part, select Copy and paste the assembly in 3-matic. Use the filled with the triangle edges to visualize the mesh. We will reduce the amount of details in the mesh by smoothing it, using the smoothing tool, which is located in the Fix tab. Make sure the Perform Post-Processing is off, as this will have a large influence on the mesh. Before we proceed with our mesh optimization, we want to inspect the quality and size of the current mesh. Use the Inspect Part tool in the Remesh menu. When inspecting the shape measurements, you can see that the quality of most of the elements is above 0.5, which indicates that the mesh is of good quality. To inspect the length of the edges, select Largest Edge Length A and change the current measure to Inspection Measure. On average, the edge length is around 1.2 millimeters. We can use this value to predict an edge length to further reduce the number of triangles. This will result in a faster calculation time in the FEA solver program. Because we have a high quality mesh, we can get a good result with the quality preserving reduced triangles tool. In this case, keep the skewness on 0.5 and set the maximum edge length of 2 millimeters, which is slightly bigger than the 1.2 millimeter we have measured before. For geometrical error, we will use around 1/10 of the maximum edge length. You can see the quality of the triangles is preserved and the amount of triangles is less dense. Optionally, you can further improve the mesh quality of your object by performing the smooth operation, followed by an adaptive remesh operation. In this case, we will leave the compensation on, but definitely play around with these parameters to figure out the ideal settings for your workflow. For the adaptive remesh, we will use the same parameters as for the reduce. Note that this is just a step to fine-tune the quality of a small number of triangles. Now we will convert the mesh of our non-manifold assembly into a volume mesh. If you want to control the inner element growth rate, select all the surface sets from the surface list and add them as local entities. For this example, we will keep the growth rate at 25, but if you want a more gradual growth, you can lower the rate to 10, for example. To visualize the volume mesh, we will use a clipping of the Y section to see the internal volume elements of our non-manifold assembly. Here you can see that the elements gradually grow bigger on the inside. Now it's time to assign different materials to the non-manifold assembly. Mimics allows a combination of volume meshes with medical images, which helps in assigning case-specific material properties. We will select the non-manifold assembly in 3-matic and take it back to Mimics. Rename the assembly and the volumes inside the assembly to avoid confusion. Hide the volumes one by one to figure out which volume is which. Then we will start assigning material properties to the L4 vertebrae. In the material assignment window, select the gray value-based method as a material assignment method. Notice that the histogram is still calculating, but we can already start filling in the material expressions. Each anatomy will have their own material expression to convert gray values in material properties. But luckily, these expressions are widely available in literature for different anatomical parts. Make sure to press apply, and without closing the material window, select the L3 vertebrae. All the expressions have been kept, and you will just have to wait for the histogram to assign the properties. For the disk, we will use the homogeneous material assignment method. The disk properties are difficult to distinguish on a CT image, so only one material will be assigned to the whole disk. With the homogeneous method, you can assign the material properties before the histogram is calculated. You can use clipping to visualize the coloring inside the volumes. Make sure the texturing is on None. Finally, export the volume mesh in one of the available formats, which can be used in other FEA solvers.